Magnetic field is in fact a region around a moving charge, current carrying conductor, on or even a magnet. In this region, magnetic effects, magnetic influences are experienced. Always the magnetic field are represented by magnetic field lines. This terminology was introduced by Michael Faraday for electric field and magnetic field as well. You see, there you use the term electric field, and here we are going to use the term magnetic field represented by letter capital B. These are represented by magnetic lines of force. You might say magnetic field lines. You see, there is a basic difference between the electric field lines and magnetic field lines. There are certain common points also, but the basic difference is that these lines are always the closed curve. That means you are not going to use the term emerges or start. You won't say. You won't say that lines of force start from North Pole. What we'll say here? Emerge from North Pole. Magnetic lines of force emerge from North Pole and enter through South Pole. That means the process is on, the continuity is maintained, the curve is closed, it's not open anywhere. At the same time, you must just compare with the electric lines of force. These will start from positive charge and this way they will be returned. Within the two charges, that means electric dipole, the lines of force are always missing. The basic difference, that's why I pointed out first of all. All other things are as usual. Magnetic field, the unit we have in SI, Newton per ampere meter, that's given by Tesla. In CGS system, this unit is replaced by Gauss. 1 Tesla is quite big unit. That's not very practical. You see, MRIs that are used these days require the magnetic field of this order, 1 Tesla or 1.5 Tesla. 1 Tesla is also equal to 10 to the power 4 Gauss. After all, magnetic field is a vector quantity that always has a direction from north to south, outside and within the magnet. This will have a direction from south to north. Once we say that magnetic field follows the law of superposition, it simply means that in order to get the resultant field at any point, we have to sum up all the individual fields present over there. This is what we call principle of superposition. Magnetic flux. I have seen many students just they feel like when it comes to flux, they feel like rocket science, nothing special. One simple illustration I'll let you know. What is the difference between field and flux? Field is represented by the lines of force and their total number is called flux. So, flux doesn't mean anything special. Flux is counted. It means the total number of lines of force have been taken into account. For calculating the flux, we have one formula. It is taken as the dot product of magnetic field and area vector. You see, magnetic field, when once you say it's a vector, obviously you'll have to represent the field by vector only. But the field might be uniform, of converging nature, of diverging nature, that have been clearly shown over here in interesting figure format. If you want to represent that magnetic field is normally inward, then you have to use this cross, and suppose you want to convey that the magnetic field is coming outward from the plane of the paper or here plane of the board, then in that case we have to follow this principle. Magnetic flux might be represented in integral formula also. This is way of writing integral formula for magnetic flux. Its SI unit is going to be Weber, and in CGS you will write Maxwell. This is Maxwell, name of a scientist. This is Weber, name of a scientist. 1 Weber equal to 10 to the power 8 Maxwell. For finding theta, you see, when you elaborate, you will write it in detail as this one. Now, the big question is, what is theta? Theta is the angle between magnetic field and surface area vector. Suppose the coil is this way, then the area vector would be pointing outward, normal to the plane of the coil. So, this is the angle between field and area vector. Suppose I am having the field here this way, horizontal field from left to right, from your left to right. Then in that case, the field is this way and the coil is here in the horizontal plane. So, we would say that the field is in the plane of the coil and theta is going to be here. Theta will be taken between A and B. So, that is going to be 90. When the field is in the plane of the coil, theta is 90, and in that case the flux becomes equal to 0. When the field is perpendicular this way, then area and B both will be having 0 angle, and in that case cos 0 becomes equal to 1. The flux is going to be plus AB. If you just turn it by 180 degree, now the angle that was initially 0 has become 180 degree. That means the value has now become minus BA as written over here. Initially it was BA when the angle was 0. You want to find the change in flux, then you will subtract phi 1 from phi 2, and this is going to be minus 2BA. And now in the last, you see, stationary charge can produce only electric field. When the charge is moving, it's capable of producing both electric and magnetic field. At the same time, you do remember that current carrying conductor can produce only the magnetic field. It's not capable of producing electric field.